Hi, everyone. Thanks for coming to the first Embodied AI seminar of this semester. We'll aim to have one every week, and there's going to be an AI social afterwards. So it's my pleasure to introduce John. John is a professor at MIT and CSIL, and he is also a technical advisor at the Toyota Research Institute. His research addresses problems in navigation, mapping, and autonomous mobile robots. He holds a degree in electrical engineering from the University of Pennsylvania and a PhD from engineering science from the University of Oxford in 1994. He is an IEEE fellow in 2014 and an AAS fellow in 2020. And John is now leading the Embodied Intelligence division at MIT, and we're really excited to have him give a talk today.
Sure.
Hi, everyone. Thanks for coming to the first Embodied AI.
I think I'm allowed to be without a mask, right?
Have one every week. And there's going to be AI social after.
So this,
so it's my pleasure to introduce John.
I call this the past, present, and future of SLAM, a personal journey. And if you know anything about me, this is really, I guess we got the Zoom windows there. Is that in the way? Let's try that. And so this is not so much a talk as my kind of life story. And I'm going to try to get 35 years into 50 minutes. And I know that task is hopeless. But just bear with me. I want to kind of tell my story. So it's a lot of pictures and stories and names and people and robots. But I hope that it can help give some context for the work my group's doing down on the second floor and some thoughts for the future. So the, let's see. My keyboard is not working. We fixed the Zoom with a trick that's not. What is that?
It's okay. It's okay.
Okay, it's not going to work. It's
okay. Let's try it
again. We're going to get rid of that. Sorry, everybody. This has never happened to me before. This is my first talk in 2 years since COVID. The slideshow, so that didn't work. Let's try this. This will work.
Yeah, there we go.
Okay, let's see how the Zoom is doing. Can you see it in the Zoom?
Yes.
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 Great. Make sure you mute it if you're on the Zoom. Okay, and I might walk away from the Zoom camera. Sorry for anybody who's remote. So first, I want to ask you a question. And so don't shout out the answer, please. I want this to be interactive if possible, but just raise your hand if you know the identity of the person in the next frame. So if you know this person, raise your hand. Okay.
I think it's Rod Brooks, but.
Oh, you're not supposed to talk. So, I'm going to mute my volume. So turn my volume. It is, in fact, Rodney Brooks with the COG robot back in 1997. I had some other older, harder to recognize pictures of Rod. And the context for my talk is that building autonomous mobile robots that can navigate around the world and understand the world and have sort of a long has been one of the central challenges of AI and robotics going back decades. And to me, Rod had just a huge impact on my career, because back when I started, there were only very few papers trying to do what we're trying to do. And obviously now the SLAM literature is very large, but there were some few seminal folks that really kind of laid out some of the key questions. And I think those questions still apply today. And so how about this person? Raise your hand if you know this person. A couple maybes, okay. Let me show you his robot. How about now? Anyone recognize the robot? Kevin's shaking his head. Okay, so this is Hans Marvik with the Stanford cart. You guys getting Zoom controls up there? Oh, that's gonna, all right. And Hans was really one of the true pioneers. Now, there were a few other early projects, kind of prehistory of mobile robotics like Shaky, but Hans did this sort of amazing undertaking of building an autonomous robot in California at Stanford in the 70s. And I have a video here. Hopefully the audio is going to come through. This is a clip of Hans being interviewed 20 years later. And so.
70s, Moravec started what he thought would be a very simple task. He hit a problem.
There were things that, although they at first looked like they might be easier because human beings do them more easily, that in fact turned out to be heartbreakingly difficult. And those were things like looking at the world and seeing what objects there were in front of the camera that was connected to the computer and moving around competently in the world, the typical robot tasks.
Each flash here represents 15 minutes of computing time.
So this was back in the mid-70s, and Hans had a single camera. He moved along a sort of slider to get 9 image stereo, kind of a 9 frames kind of stereo system. And the processing was so slow that he needed to wait 15 minutes each time the robot moved. And so, Yulan, if you can mute anyone else who's on the call, because there's some noise coming through. And so here's a few other folks. So does anyone, raise your hand if you know any of these 3 people? You know 1, if you know 2, if you know all 3. So this is Raja Shatila in the back from Las and Toulouse, a true pioneer of SLAM. Hugh Durant-White, who is my advisor, and Sebastian Thrun, who obviously is very famous via the Google Car project and many other endeavors. And this was in 2002 at something called the SLAM Summer School. So SLAM became a very hot problem 20 years ago. And a lot of the folks in this picture, we had about 10 instructors and 50 students. They become dear friends, like Wolfram Burgard, who I met, I think, just before this. Like Mike Montemerlo is a student here. He's now runs all the mapping and localization for Waymo, the Google self-driving car project, is my understanding. And if you bought stock in SLAM in 2002, it would be a bit like buying stock in Apple or Google. Like it's a problem that grew very large and had a lot of dividends. Now I'm very indebted to my advisor Hugh Durant-White, and I really very much think like a PhD is a journey. And I actually have this book, How to Get Your PhD, a guide for the journey, and it's someone published last year. And I think that I was one of Hugh's first 2 students. He wound up having about 70 PhD students over sort of a 15 to 20 year period. And this is us a while later in Australia, where he is now. And I really think of the PhD as a journey. And I want robots to have journeys. I want robots to have long-lived autonomous existence. And so for me, my journey, I was at UPenn as an undergrad. Did something called lightweight football. That's with my best friend who played for Navy. They had just beaten us 56-0. And so he's smiling a lot more than I was. I had lots of friends. This was on the roof of the engineering building. We'd be in trouble if we got caught. And then I went to Oxford, and I was very fortunate to get a fellowship there. And I got to interact and meet with all kinds of folks from all over the world. And just that joy of being a grad student, I feel my heart is broken for COVID and the impact on students everywhere. But I do encourage you to meet folks and be part of the journey, and it's the people you meet. But I spent a lot of my time working in the lab. This was in the basement at the Jenkin building, had a desk up on the 2nd floor. And this was one of the first Sun workstations in England. I had never programmed in C. When I went to Oxford, the box next to me is a computer vision processor called a data cube that cost about $100,000. And it could just barely do edge detection at 3 frames a second. And so the state of computer vision was really in its infancy. And so I'll come back to that. I was fortunate to come to MIT in 1991. I've truly found paradise. Does anyone get that? Violet gets it, right? So I truly did, and I think I came here to do autonomous underwater vehicles. And I think that thinking about autonomous robots, when you want to try to do things underwater, where there's very poor communications, where there are great consequences if something goes wrong, it really is a sort of a way of thinking, a kind of a mindset. And so one way I was thinking about it, I brought a bunch of coffee mugs, but for the Zoom, I'm doing it with pictures. I'm involved in many communities at MIT. So flash forward to today. So I'm part of the mechanical engineering department. I'm part of CSAIL. I'm thrilled to be part of the lab. I'm very active in the Woods Hole Joint Program. I'm associate director for engineering. I'm part of the community with the economists like Frank Levy in the back and the Work of the Future mobility initiatives. And I'm also fortunate to be part of Toyota Research Institute. And so am I allowed to call this a mugshot, Frank? And so part of the challenge of my life is drinking from 5 different coffee mugs at the same time, like this sort of that. And it's one of the real thrills of MIT, this sort of interdisciplinary, interconnected culture. But I'm fortunate, but it also might, why I'm a little frazzled sometimes is a bit too many things going on at once, and my students know this well. But what I want to do is talk about some of the history and challenges of mobile robot navigation, and then give a little window on our current research, inference and representations for spatial AI, and then some open challenges and future prospects. So I'm going to go pretty big on the history part. I hope you guys don't mind, but the moral of the story is I think originally we wanted, remember when Moravec talked about objects in the world? We wanted to have a sort of object-based understanding of the world. And for various reasons, we got away from that with something called Posegraph optimization, which was a wonderful, impactful way to have your robot traverse large areas, build maps, do cool things. But simply estimating the robot's trajectory falls short of achieving a true understanding of the world. And so we're revisiting some of the old questions equipped by modern tools, machine learning, robust inference. And so this is sort of almost like an introduction to our group, to folks that other folks here in EI, we'd love to interact with you. So, so some history and challenges. So if we open up this book, it talks about, and obviously this is hard today with the era of Google Scholar and Archive, but defining the literature, think of like this inner circle of the 5 most important papers related to your thesis. For me as a student in Oxford, and I'm sorry at 56 years old to be like in the good old days or the bad old days, you'd have to walk down the street to the library and see if it's open and have enough 10p coins to use the copier and find the proceedings and copy a single paper and then anxiously read every word on your way back in the rain. And it's a lot easier now to sort of, there are many more papers, it's easy to get them, but try to define that sort of, that bullseye of what a PhD is, a conversation with the literature. And for me, that conversation with sort of 3 to 5 key papers, one of them was Rodney Brooks. And so Brooks wrote a paper called, I gotta get rid of this Zoom window, let's see. Oh, it's not helping me, okay. So aspects of mobile robot visual map making. And Rod sort of foresaw the trajectory of probabilistic robotics, and he took a different path. But he said, mobile robots sense their environment with error-laden readings and try to move a certain distance direction only to do so approximately. Rather than try to engineer these problems away, it may be possible and may be necessary to develop map making and navigation algorithms which explicitly represent these uncertainties, but still provide robust performance. And so when I went to Oxford, 1987, I had been working in a General Motors factory the previous 2 summers. They had to put in cables in the floor for the robots to follow. And I said, we want robots to navigate the way people navigate, using the sort of geometry of the world. And Hugh and I shared that vision. And so some of the things that Rod says in this paper, the key idea is a rubbery and use a relational map, which is rubbery and stretchy, rather than try to place everything in a rigid 2D coordinate frame. Rod also said, these problems are far from solved, and much remains to be done to produce complete solutions. Now, 20 years ago, a lot of my friends and colleagues in this subcommunity of mobile robotics thought SLAM was solved. And it's almost kind of old-fashioned, or I might be considered having a lack of curiosity or a laziness to be still working on this. But I think there are still some core challenges, and I'll try to explain why. And the SLAM problem is a beautiful problem because I think of it along these different axes of difficulty. So one, like many AI problems, is about representation. How do we represent the environment? And another axis is how do we do inference? Do we represent uncertainties with Gaussians? How do we solve data association? And then how do we build systems and make them autonomous? I was fortunate as a grad student, I was funded by a European project my last 2 years where we had to fly. I made 10 trips to Paris as part of a a project where we had to do demos. They had robots there. I would make my tar cartridge, use tar to make a 1/4-inch cartridge, fly over with my code. There was no, way to remotely access things, maybe FTP, jump through a lot of hoops, and to try to do demos and to try to make it work. And so the other kind of choices representationally, I think, occupancy grids. So Maravik, who I mentioned, went to Carnegie Mellon, and he collaborated with Alberto Alfez, who sadly passed away in the past 2 years. And they came up with something called an occupancy grid, which was an alternate representation, a bit like a sheet of graph paper where you sort of fill in your sensor data. And in effect, this was an implicit representation. I think things like TSTFs and NERFs, they're sort of like parallels to the future. I hated occupancy grids. I wanted to get something that could really be more isomorphic with the world. I want to capture accurate geometry. And for that, I turned to France, to Rajesh Shatila, who was an early pioneer in robotics in France. And the school that came out of his lab was to try to explicitly represent uncertainties in geometry and connect that to path planning. Now, another important paper that appeared was by Smith, Self, and Cheeseman, who basically latched on the concept of networks of spatial relationships, and has a lot of this connects to local versus global reference frames, making relative measurements, and how you can sort of stitch together relative constraints to build up a global model. And this was very, very influential. And Hugh had similar ideas around the same time in his thesis from UPenn. And so the essence is we have a robot that starts at some location. We could just call that known, or maybe with some uncertainty. You observe some objects. There are uncertainty in those measurements. We move. There's uncertainty in your motion. You re-observe, say, the first 2 objects and observe a new object. How do you combine these uncertainties over time? And try to do that in a way that kind of can generalize to large areas, changing environments. And so this kind of problem was like, it drew me in, and I became addicted to this problem. And we're still kind of working on it. And so you can formulate this as a maximum likelihood estimation problem with some appropriate state space representation for your robot pose or trajectory and landmarks. Now, if a key challenge, though, is when we have uncertainty about the observations, which measurements go with which features, it can give rise to non-Gaussian distributions, and that makes inference really challenging. And so what I tried to do is, this is a screen capture video for a replay of an experiment we did at Oxford of using Polaroid ultrasonic sonar measurements to make predicted sensor measurements to a map. This is just given a map, can you localize yourself? And as a student, I worked on that problem, and then also given if you knew your location, how would you build the map? And a lot of it comes down to having a good sensor model and being able to predict which measurements you can trust, which ones are outliers. And we had this notion of sort of geometric beacons. Could you use sort of the geometry of the world as landmarks? And so this is a demo we did in France. The top shows just the dead reckoning of the robot, just integrating the wheel encoder measurements, and the robot kind of gradually drifts off course. Whereas with our code, we could run the robot in a sort of continuous loop around the lab, which made the sponsors happy. And so we did it on multiple robots and multiple labs. We also showed how if I knew the position, and this was like measuring on the floor with a tape measure, establishing a coordinate grid, you could actually map the features of the world from the sonar. But we couldn't put the two together. And I decided it was time to graduate and try to come back. And so the essence of SLAM is it's a sort of which came first, the chicken or the egg. If you knew your map, you could estimate your motion. If you knew your motion, you could build a map. How do you do that concurrently? And so that's sort of the essence of the problem. Now, a big issue that we still haven't properly dealt with, in my view, in the community is that the environment changes. And this is one thing that can lead you more towards a Posegraph representation where you could do loop closing based on aggregates of data rather than looking at individual objects, which gets very tricky when those objects move. And so one of the papers in my thesis was for the IROS conference in Japan in 1990, which we kind of formulated a dynamic map building process where you would add in objects as you see them, but then remove them when you didn't see them. And this was still sort of very much in its infancy. So this conference called IROS, Intelligent Robot Systems, primarily was a Japanese conference, early days. It's gone more global. We just had the IROS deadline last week on March 1st. So everyone in my group is kind of exhausted. We had a bunch of IROS papers. I'm exhausted. And, but it is in Japan this year. It's in Kyoto. So if you'll forgive me, and I know I'm going to run out of time, especially because of the Zoom issues, I did a little flashback to my first big international conference was IROS 1990, north of Tokyo, in a place called, it's going to let me do that? It's not going to let me do that. Okay, well, maybe at the end, I have some pictures of going to Japan back in 1990. And one of the things that really inspired me as a student is Rodney Brooks was giving a talk at that conference. So I actually met Rod in 1988. ICRA was in Philadelphia that year. I'm from Philadelphia. ICRA was in Philadelphia again this year. There's sort of symmetries and parallels. And when Hugh and I came to ICRA, we visited MIT. I went to the sort of ivory tower of Tech Square where the AI lab was. And Rod Brooks and his new student named Colin Angle, who happens to be the CEO of iRobot, they took us to a place that had just opened called the Cambridge Brewing Company. And I tried to argue with Rod about why robots needed to make accurate maps. And he completely had turned away from all that. So I thought for 2 years when I'd next see Rod, what question would I ask him? And he said, when will you build a robot that knows its position? And he answered, he said, I don't know my position. And so, but I'll come back to that one. So anyway, okay. So I got to come to MIT to do underwater vehicles. This vehicle, where's a picture of the Odyssey? This one was a postdoc and research scientist for 5 years. And then I got to go cool places like the Arctic, like the Pacific Ocean, getting really seasick, trying to put robots in the deep water that didn't want to go in the deep water. Experiments off the coast of Italy. There's a long version of this where I play the videos. I think it's lots of fun, but I'm going to get to the math and the more modern part soon. But so in terms of the chronology of this story, student in the late 80s in Oxford, came to MIT. Actually, SLAM kind of stagnated because we didn't have good sensors. The sonars were kind of hopeless. Computer vision was still immature. What happened in the late 1990s was this thing called the SICK laser scanner came out. And the SICK laser scanner gave high quality sort of 2D planar laser data that suddenly made it more feasible to map large areas. And we got involved in that. And we still wanted to do computer vision, and that came along a bit later. And so this was the 2002 SLAM summer school. We had another one in 2004. I don't know if anyone recognizes any people in this picture. Matt Walters, yeah. And so this person here, Matt, was one of my students. Matt was the champion of the espresso machine on the 3rd floor. And so we're getting an espresso machine on the 2nd floor, as we said on the Slack. And this person, anyone know who that is next to him? So that's Ryan Eustace, who's another former student who's advised by Henu Singh, and I was his co-advisor. Ryan is the head of the driving team at Toyota. And that's Paul Newman from Oxford, who was my first postdoc, just an incredible person, Andy Davison. And so what I'd like to do in terms of the story is you kind of need to insert 20 years of research here. And so like Frank Dellert and Michael Case and I say, and Andrew Davison and Visual Slam, Wolfram Burgard and GTO and all sorts of great things, Juan Domingo Tardos and Orb Slam and Data Association. But from this perspective of personal journey, if I go back to this sort of representation, inference, systems, and autonomy, effectively, we've done this exploration of different types of representations, so metric versus topological maps, rich dense models like TSDF models, trying to pull in more object-based models, say the SLAM++ paper was an early attempt, and trying to really understand the world in terms of more descriptive terms. And we collaborated with biologists who think about how the difference between like allocentric versus egocentric world representations and how you put that all together. And SLAM is interesting as a very high dimensional, ever-growing state estimation problem. And solving the data association problem is a really hard part of it, like which measurements correspond with which features, which can be discarded. And more recently, there's been a lot of work on learning for SLAM. And in fact, when I visited Matt Walter in Chicago, I think it was Guy in the audience. I'd given a keynote talk. I was out of breath at the end. And I told some of the story of the SLAM inference. And Guy said, hey, I'm from the physics department. Why don't you just train a deep network, just collect some input data and some output data, and don't worry about all this stuff. Who cares? And so he broke my heart. And it's probably the first moment when I was like, my entire career is going to be thrown away because of deep learning, which maybe happens to a lot of academics these days. But it's also important to build systems and make them autonomous. And so how do you couple perception to planning and control? And we want to close the loop, and we want to put systems in the world and be able to predict their performance and know when they're going to work and when they're not going to work. And so with all due respect to the deep learning community, there's a long way to go from like tables of numbers for like performance on standard data sets versus actually putting your robot in the world. And so how do you go from demo to deployment? And so from a more personal aspect of what happened, say from that 2002 timeframe onwards, I've advised or co-advised 24 PhD students and so many gifted programmers. Ed Olson made these videos. Ed was one of the early proponents of a Posegraph optimization approach. This video is kind of cool because the vertical axis is time. And this is on the 5th floor, I think, of Stata over by Gates. And it's showing how if you go around and you traverse back to the same area, these red lines are constraints, loop closure constraints. If you have a laser scanner and you can match one scan from another, you can take out the dead reckoning error between those poses, and you can build a more global representation. Another example is sort of a famous data set we took, Michael Bossa and Paul Newman took with me, the Killian Court data set, which is on the 3rd floor over on the main campus. And an example of this, trying to close large loops. And we, and the thing is, when we originally tried Killian Court, we weren't using a full Posegraph. Michael Bossa had a technique called the Atlas approach, which was a network of submaps. Within each submap, we try to do more geometrical feature processing and then stitch them together in a more topological network. And so actually, so here's Ed Olson's thesis, one of the early Posegraph theses showing that data set superimposed on the part of the campus. So my Ocean office was over here, my Meki office is here. Since the first day I set foot on campus in 1991, I wanted to close those loops, and it took us over 10 years. But actually going back in time, the first time we did this, and this is with Paul Newman, Michael Bossa, this is another early AI pioneer, Ben Kuipers, and sadly our dear colleague Seth Teller, who we missed dearly, who was Mike's co-advisor. And Mike's approach could process this data in real time, closing large nested loops, which was pretty remarkable at the time. But one of the challenges we had is when you're trying to reconstruct the geometry of the hallways and you come back, it's very easy to get a sort of feature doubling problem where you might get a slightly offset kind of corridor. You don't get a model that's isomorphic to reality. You kind of have this, we needed another, it was robust enough that it could work, but it was still a little bit fingers crossed because getting the geometry of the world to match all the time was hard, and even more hard if things changed. So, and then another somewhat more recent example, my student Hardy Johansson from the MIT Woods Hole Joint Program who did underwater mapping. This is using a PR2 robot on the 2nd floor downstairs. And here it's using stereo vision. And so the same sort of approach, but now using stereo vision to get features and to kind of navigate around and build a map. Now, and this is the kind of SLAM that was kind of considered solved 10 years ago. Skydio, the drones that Frank Dellert helped start, and Nick Roy's students, they're a great example of a commercial product that effectively has this kind of capability embedded. And it's easy to make maps that look nice and have a robot that can navigate a pretty long time and further map every floor of the building. But there's still something missing is kind of my view. And so now, in terms of this, like, insert 20 years of history, the SLAM summer schools went dormant for over 10 years, but Carnegie Mellon resuscitated them this year. And there's a wonderful set of great talks online, and definitely like Andy and Luca. And so there's a lot more to kind of find out. What I want to do next in the next part of the talk is to tell you about my current research group and some of what we're working on. And to me, I had these kind of guide stars towards long-term autonomy, shared autonomy. And the students I found at MIT hate to be told what to do. really hate to be told how to do something. So a lot of it is sort of pick the guide star and try to establish the conversation to guide people to explore interesting parts of this multidimensional space, and hope that, and just sort of trust the MIT system that the students here are so amazing and self-driven, and by working together, they learn so much. So sometimes I talk about using Jedi mind tricks to try to persuade my students or plead with my students to do things. But here's Violet, Odin, Mark is from the joint program visiting us. Melody studies penguin behavior in the Antarctic. Chad, Carol, Curran, Kevin, Yihao, Zichi, and Alan. Few folks missing. Brendan is a naval officer. He's actually a commander, but he's wrestling with undergraduates. He's off at the wrestling championships this weekend. And Jesse just finished up. He's a naval officer, lieutenant, and a few other folks that just graduated or finished. Nicole and Sophia, Amori, so a couple of UROPS and MN students. And we like to build hardware, but we want to do things that have a physical embodiment, but we obviously want to work on sort of publishable algorithmic and learning contributions to try to get into the top conferences. And obviously, if you look at robotics today, so this is a picture of Alan. Is Alan here? Testing some ultra wideband localization for multiple vehicles. So cooperative localization is the theme. This is over in the Ability 31 mocap. And so at the risk of sounding critical for the robotics community today, I'll have to admit that if I could travel in a time machine back to, say, Rodney Brooks in the 80s or Hans Marvik in the 70s, I can't help but think they'd be a little disappointed if they could travel in a time machine here, because I'll tell you an unfortunate truth about robotics today is many of our robots kind of sit unused a lot of the time. It's actually very hard to do demos, and we don't have any robots that have this kind of ongoing autonomous existence. And whereas sometimes with ROS package updates and things, like a demo that works on Tuesday might not work on Friday, And so I think that what I'd like to try to do is to get us, the embodied intelligence name actually partly comes from Rod Brooks had a class here, Embodied Intelligence, where he talked about the importance of building physical systems that close the loop. And I would love for us to get back to that. You could have a conversation. Can you still publish papers at ICRA, CVPR, if you spend too much time doing systems? But our vision was to try to, with RSS, Robotic Science and Systems, which is both a class and a conference that some of us helped kick off, is to try to build systems that lead you to the science and build and test the science. And in robotics today, many folks use motion capture systems. Many folks use April tags to take away the perceptual uncertainty. Many folks use simulation. You can do a whole robotics PhD today and never leave Mujoko. And maybe that's what the community needs, but I kind of feel like we got to work on that physical embodiment. And so just as a quick snapshot of what we've been working on, it's sort of painful to pick which project to talk about, but I picked Zichi's, and I'll explain. So we've written a lot of IROS papers. This is going to be way too much text, but just to give you a sampling of the kind of things we do. So we have a paper on AUV-assisted diver navigation. We want to work how an underwater vehicle could actually be a navigation aid to a scuba diver that's doing a mission in an environment with very poor visibility where it's difficult to surface for GPS. Chad's working on nested sampling for non-Gaussian inference, and in general is trying to explore new state estimation techniques. And in fact, one of the places that we drew some useful inspiration and very effective packages is from astronomy. So it turns out trying to process data looking for exoplanets and processing these massive challenging space data sets are leading other scientists to explore more general non-Gaussian inference for higher dimensional systems. And I think that's actually useful for robotics. Zichi's work, I'm going to talk about more in a second, of trying to use SLAM as an aid to help improve object detection, object pose estimation. Carol is collaborating with Elon on using neural descriptor fields for change detection for objects, for things like coffee mugs. Curran's working on active navigation to try to actively disambiguate ambiguous situations. And Kevin, along with my former student, our great collaborator, David Rosen at Northeastern, looking at spectral measurement sparsification for Posegraph SLAM. And so we're sort of running the gamut of some of the algorithmic issues of how to do the inference efficiently and robustly and explore new techniques, with also trying to pull in new machine learning based sensing. We do have a few ICRA papers accepted as well. So spectral initialization, Kevin and David, and then a cooperative range-only planning for Alan. And so a few other things submitted to conferences we shouldn't talk about. And but I'm just going to give you a little snapshot. So like think of this as like this long history, some context, and then I'll give you one example, and then hopefully try to pull it together at the end with a sort of story for the future. So we're looking at trying to develop semantic representations to improve the robustness and efficiency of navigation. So it turns out if you use dense 3D point clouds, that's very, it doesn't give you a readily accessible, editable representation of the world. And so I think that representing the world more in terms of objects or human level terms can both be more robust, more efficient, and can lend to better cooperation with humans. And so kind of where am I? What objects are around me? And for example, how do you deal with very ambiguous objects? And this is partly motivated by COVID. First, asked Zichi to look at trying to do SLAM with playing cards that have an ambiguous, a 180-degree flip ambiguity. That may seem like, why is that a big deal? But if you see something like a 10 of hearts and your robot comes back the other way and sees the 10 of hearts from the opposite direction and doesn't have some sort of awareness of the symmetries or the ambiguities, it's going to cause your estimator to blow up. So that's a paper we had at IROS recently. And let's see. And in general, so I'm going to use some of Kevin's work to kind of motivate. Kevin is in the joint program, cares about underwater mapping. And a lot of times the underwater environment is sparse. We have very poor communications and there's a high cost of failure. And so our trend is kind of going back to basics. So sort of like, this is like a 30-year-old slide, how we pose this estimation problem when we bring in ambiguity about the objects, and in particular in a semantic SLAM problem, we have not just identities of objects, but also categories. So I brought along a bunch of coffee mugs, but for the Zoom people, I won't walk away and grab them. When I was a grad student, I was so obsessed with SLAM, I would be in the pub in England and I would bore the hell out of my friends by lining up the pint glasses as if they were landmarks and trying to navigate through them. And I think there's something just like that very sparse, small number of objects, highly ambiguous situation problem that we still need more tools to understand. So hopefully new tools in inference and estimation can help us and sensing can make us make progress. So if you're doing a PhD thesis, a great question is, what is the thesis of your thesis? I've heard Daniela ask that question, and Kevin, I hope you don't mind me telling them how can we develop systems that can operate long-term, learning and maintaining an economical semantic representation of the environment, backed by the robustness and mathematical rigor that we've come to expect of autonomous systems. And so that's sort of a really good sort of guide star question for us. So when we formulate this maximum likelihood estimation problem, one of the key things of making it a semantic problem is we're going to bring in categories of objects, and we have to solve for the data association. And this is an example from the Kitty data set from one of Kevin's papers from 2 years ago. And I don't have time to go through all the detail, but just to give you a little bit of context for this, Kevin talks about this balancing act between efficiency and robustness. If we didn't have a real-time robot that had to navigate in the world and make decisions, it could do something more sort of computationally intensive to sort of have more, quote, thinking time in terms of trying to resolve the situations when things are ambiguous. But if we want the robot to be actively engaged in the world, closing the loop, we want it to be efficient. And so how do we achieve the balance between robustness and efficiency? And a lot of folks have thought about related problems in this domain. And in terms of coupling semantics and navigation, I mean, to be honest, for like the recent state of the art, we need no go further than MIT for Luca Carlona's group with Chimera and some of their other newer publications. Extremely strong work on semantic fusion so trying to do. Andrew Davison's group has semantic fusion, for example. how do you kind of bring in richer geometric descriptors of the world and couple that to robust estimators. SLAM++ was a pun on C++, of taking SLAM and making it object-oriented in the way that C++ is an object-oriented version of C. And Andrew Davison's group proposed that, gosh, 9 years ago, and they could navigate based on, say, chairs at Imperial College. There's been more work in this area, but it's still only scratching the surface, we think, of what's possible. And then there's some great work, say, out of UPenn, Tanisov and Bowman on trying to couple probabilistic data association with semantic SLAM. And so the essence is, how do you handle multiple hypotheses? How do you create a system that can be tolerant of ambiguity? And ambiguity arises very naturally in situations where you have perceptual aliasing. Now, historically, in what we're about navigation, loop closing was often a big motivator for handling, say, outliers or mistakes. And so max mixtures is a method Ed Olson developed, switchable constraints, Sunderhoff and Protzel. My former postdoc, Michael Case, developed something called multiple hypothesis ISAM2. It's a lot to explain, but basically an algorithm that can keep track of multiple hypotheses. And the challenge is the curse of dimensionality is lurking behind the scenes. Once we start allowing multiple modes of uncertainty, if we can't efficiently prune the tree of hypotheses over time, we're not going to be able to achieve real-time performance. And so Kevin's developed a series of papers, and one is going back from 2020 using a max mixtures representation of uncertainty. And he's got a great talk on this online in the Tartan Slam series. I'll skip that for time, and I'll skip the ambiguity aware. What I wanted to do now is, with that as a little bit of context. So we're working to build these object-based SLAM systems, and we want, and one thing that sort of really almost disappoints me in 2022 is it's really hard to get good machine learning detectors for objects. So I'm just going to briefly show you a sampling of Zichi's work, where we're using, and there's some on the table over there, the YCB objects are very well kind of studied, the spam, sugar box, Cheez-It box. And the basic idea is, can we have a domain gap. If you train a detector on one data set, say the YCB imagery, and then say a detector like DOPE, which is one of the state-of-the-art detectors from Dieter Fox's group, and you apply that, say, in the lab here in CSAIL, its performance is not going to be that great. There's a domain gap. And the idea is, and manually annotating images for every new domain is tedious and sort of doesn't really scale. So what we'd like to try to do is to use SLAM, use the location cues from our SLAM system to automatically improve the object detection system. And so here's an example of the kind of pre-trained DOPE model here, and that should play in a second. And so I'm going to keep this a short version, and we can talk to Zichi afterwards with any questions. But if you just take a camera and go through the world and run a state-of-the-art detector, unless it's sort of like a self-driving scenario where there's lots and lots of training data from a target domain, it turns out in a robotics application, most detectors aren't really that reliable, and it's not at the point where we could sort of turn a robot loose using them. And so the idea is to use the pose predictions from a pre-trained detector, even though they're not perfect, combine it with some odometry, in this case using OrbSLAM, and to develop pseudo-labels so that the algorithm, the SLAM system, can help the robot generate more labeled data in a self-supervised way, creating pseudo-labels to try to detect the object. And so getting optimized object poses out. So this is the kind of input imagery on the upper left here is sort of a typical detector running for, say, the spam cam, and you can see all the mistakes it's making. And this is the output with optimized object poses. And an important part of this is how you get the uncertainties to use this. And so in comparison, another kind of a companion part of this paper is an automatic covariance tuning method in which the algorithm can effectively set the right uncertainty estimates for the detector that it's developing. So let's see. So just to sort of jump to the kind of, so basically we formulate a joint optimization loss that effectively can try to optimize both the SLAM variables and the noise covariances, and then attack this with an alternating minimization approach. And it set up a pipeline for self-training of the system. And so let me show you, I can come back. I'm going to show you the video to make sure I get it, and then I can maybe come back and explain a little bit more if I have time. But effectively, we did experiments. I'm going to show you this one first, actually. So here's some experimental results on YCB. And so the left is the pre-trained dope detector, and on the right is the self-trained detector that's using automatically generated pseudo-labeled data from the pose estimates. And the take-home message here is to see how jumpy and skittery the object detections are on the left and how stable they are on the right. We've also, and these are very short sequences. What we really need, I think, as a community are much longer sequences of data. Here's an example. It's very simple, single objects like sugar box, spam can, Cheez-It box, but in the mocap in Stata to effectively traverse around an object and train the detector. And then using the trained detector, it can do a much better job of pose estimation. And so we have a paper, we just put it on archive, and which shows the results for this kind of self-trained procedure. Yep. And coupled with the automatic covariance tuning method. So I realized I went through that a little quickly, but what we'd really like to do is to can the fact that we have a robot that can actively move in the world, that can take lots of data that is sort of causally related to in time. A lot of the kind of ImageNet style training on the internet, it's like a million random images from all over the internet, which is obviously really cool and powerful how well it works. But I think a person or a robot or an animal has this kind of continuous engagement with the world that you can leverage the motion cues and actively move to disambiguate data. So my dream is a robot that I could put a bunch of objects down, and the robot could learn about those objects and be able, say, to manipulate them. One big application would be mobile manipulation for some of this work. Okay, so all right, and we have one other one. I wish I had more time. We also have work on coffee mugs and changing them. So Carol's work with Yulon. I'll talk about that another time. So let me just try to wrap up in the last few minutes with sort of open challenges and future prospects. So I feel that truly robust object-based SLAM has been elusive. And long-term autonomy in highly dynamic environments is still an open, hard problem. And I would like to create a robot that can learn over its lifetime with the ability to recover from mistakes and improve its performance over time. A lot of robots, it's kind of like a fingers crossed situation. Like when it works, you make a video of it and if you run the robot longer and longer, it doesn't get better. It's actually just a higher probability that something's going to go wrong. I also believe that shared autonomy is important, where we can develop robots that can better interact with people. And I think these representations can kind of lead us down that path. So just in a future context, I follow Jan LeCun on Twitter, and obviously he's a giant Turing Award winner. And I found he may mean completely different things with these words, but he's recently posted about the importance of having the ability to learn word models and for systems to be able to make predictions. And a key part of the sort of SLAM enterprise is making predictions about the world that can be tested and changed. And so, I actually want to go back to Moravec, kind of back to the beginning. In his famous Stanford CART CMU rover paper, he talks about, with the evolution of natural intelligence, we believe that incrementally solving the control and perception problems of an autonomous mobile mechanism is one of the best ways of arriving at general intelligence. And a universal feature that most impresses me in this context is that all animals have evolved perceptual and behavior competence comparative to that of humans that have evolved, first adopted a mobile way of life. And solving the day-to-day problems of developing a mobile organism steers one in the direction of general intelligence, while working on the problems of a fixed entity is more likely to result in very specialized solutions. So I think we have to turn our robots loose into the world, try to get away from bolted on the table with a mocap overhead. Can we have robots that go out in the world and discover their own data, teach themselves, fail, and recover? So in conclusion, I do remain optimistic on sort of this basic university research in robot navigation and mapping. Some folks say, oh, isn't this all getting solved in industry? I think there's always room for the sort of the PhD student that's thinking obsessively for a few years about a problem. There's a lot, there's still pretty open questions here. And where am I and what is around me is timeless. Rod Brooks said much remains to be done to produce complete solutions, and I believe that is still true today. And what representations and inference techniques enable robust long-term autonomy, and can we enable lifelong self-learning in dynamic environments? And ideally symbolic representations that can enable human-robot interaction to really bring out the best of human and machine working together, helping one another. So I'll stop there. That's time. Any questions on the Zoom? Anybody? Any questions? Hello. Yeah.
Can you know any advances in the past 5-10 years that you were surprised that it worked, and or something that you surprised it didn't work?
Let's see. I thought that object detection would be better in terms of like you look at something like YOLO and you see, wow, but for 3D pose estimation, it's still really hard. That's what I would say. Some things that have worked, not so much that I've been surprised, but I'm very interested. Can I put you on the spot? Do you want to tell us about Grad Slam, for example? So I'm sorry, do you want to introduce? So he did some cool work called Grad Slam. That kind of surprised me. So do you want to tell us about it?
Yeah.
I can repeat.
Thanks for that.
Yeah.
Come
on up. So this is a fully differentiable. Let me explain it and tell me, you come up, tell me if I get it wrong. So basically trying to create a differentiable SLAM pipeline so that then you can do optimization. Is that sort of the key idea of Grad Slam? And I'm sorry, tell me your name, I'm blanking. Krishna, yeah. So Krishna's from Montreal and he just got here, right?
Right.
And but we need a differential pipeline where you can add in maybe the objects. Is that possible?
I think so, but there's a lot of work to be done in that space. So
Yeah.
That's something I'm excited about.
Cool. All right. Thanks. Sorry for putting you on the spot. Any other questions? Any other questions? And if you got to run, I totally understand. Good.
Another question, like the iRobot, like vacuum robots, has been like super impressive. Like they share like maps between like different robots.
Yep.
And they kind of one follow the other.
Yep.
And it looks like they have like good applications. Like any comments on that?
No, it's a great success story. Yeah, it's like it took it was a 20-year overnight success story. God.
So like if you were to build something like in C-scale, like what's an application built for lifelong?
How about a robot that cleans up all the coffee mugs downstairs after we install the coffee machine? By the way, everyone's going to have to clean up themselves, or we can't keep the machine. Any other questions? I have a funny iRobot story, but maybe it's not going to work. Yes.
For a fully probabilistic treatment of either the existence of objects or changes in object positioning, where you're doing inference over the full distributions of those sets.
That's a great question. At some level, we're trying to do it, I think, at some level. The challenge is the dimensionality of the kind of space. Zichi, do you have an answer to that one? Or Chad?
The problem with the form, this works, but that doesn't. 10 objects, 2 of them moving. We've got that to work in real time for the last 3 years, but 20 objects, I'm just making that up. But, the boundary of practicability.
Yeah, no, that's a great question. So we can do a small, let's see. Currently, we can sort of do the YCB objects. We can do coffee cups, fingers crossed. And I think that one challenge is, what are the objects in this room? Like, is the whiteboard an object or is it part of the wall? The table, the chairs, the table legs, the backpacks. What about a couch? What about like cushions on the couch? Deformable objects, objects that move. We've tried to, for example, automatically detect objects by detecting changes over time. But there's, you get into this almost philosophical question, what is an object? Should we stop?
Yeah. Okay. Yeah. Thanks everyone for coming. And there's food on the right.
Cool.
Yeah. Thanks, John, for giving us such a good talk.
My pleasure.